Welcome to BVS Pragati channel. In this session, let's have a look at some more design considerations of MMIC broadband SPST switch using MESFET. So we are trying to understand how a SPST switch can be designed using only one single series MESFET. Okay, so here the MESFET is used in series configuration. Okay, in the series configuration, if the MESFET is turned on, then the RF signal has a path from the input to the output. And if the MESFET is turned off, what happens? This is open and RF signal will not have a path from input to output. So during the on state of the switch, insertion loss is very important, and during the off state, we'll look at the isolation. So what does insertion loss means? So for example, if there is a 20 dB RF signal over here, it should appear with minimum loss at the output. So if the minimum insertion loss is 1 dB, that means at the output at least we should be able to see 19 dB of the RF signal. Okay, so with this switch, will this be will the insertion loss be completely zero? No, because this MESFET is not an ideal device, right? So it also has capacitive effects. So it's not completely resistive. So because of that, the insertion loss is non-zero. So there's some shunt capacitance and there's also some dissipative loss. So for a single frequency, what we can do? We can actually eliminate the internal capacitance by parallelly resonating the circuit with an inductor or a parallel short circuited stub. What if? So will this method be helpful as the frequency range increases? No. So as frequency range increases, you cannot have an equivalent inductor value. So for that reason, there's one practical solution. So what is the practical solution? And will this practical solution work if the bandwidths are above 20 to 30%? So the practical solution is to place the MESFET across appropriate inductive transmission lines. So the length of the transmission lines can be adjusted to compensate for the effect of MESFET capacitance without significantly affecting the performance of the design. Okay. So what about bandwidths about 20 to 30%? So if the bandwidths are about 20 to 30%, this compensation is also not sufficient. Then the complete SPST switch needs to be optimized to improve performance, and for that you can go for cascaded series and shunt diode sections. Okay, now let's have a look at the MESFET model in the on state and off state and the various values related to on state and the off state. So this is the MESFET model in the off state. So you have C off, R off and CP. Okay, C off is CDS, R off is RDS, CP is the parasitic capacitances, and in the on state you have R on, L and CP. Okay. Now let's have a look at the FET widths and how the values change with the increase in FET widths. So as FET width increase, we see that the amount of current that flows in the FET is more, hence the resistive effect decreases. So you see for a 600 micron FET, the resistance is less. Similarly, even in the on state, we see that as the FET width increases, the resistivity reduces. Okay. Now how about the capacitance? It is equal to epsilon naught A by D. So that is epsilon naught width into length by the depth. So as width increases, we see that the capacitance value increases, C off increases. Similarly, how about the inductance? That is the parasitic inductance. So that reduces as the FET width increases. And how about the parasitic capacitances? That also increases with increase in FET widths. Okay. And in the next session, we'll have a look at how we calculate the insertion loss and the isolation with respect to each FET width. And we'll also discuss about how we are choosing the configuration, how we are cascading series and shunt sections to achieve the performance. That's all for this session. More in the next session. Thank you. Thanks a lot and I wish you all the best.